formula we're going to learn today. So this says we know that a geometric series is just the sum of consecutive terms in a geometric sequence. 3, 6, 12, 24. What's my common ratio for this example? What am I multiplying by? I'm multiplying by 2. So it says if the common ratio is greater than 1, we will keep adding larger terms so the total can get big in a hurry, right? If I tried to keep adding on terms, now I'm at 48, then I'm at 96. It says using the pairs doesn't do us much good because the pairs will have different sums. So even if you look at these first 4 terms, the 3 plus the 24 would give you 27, but the 6 plus the 12 is only 18. So the pairs don't work for a geometric series the way they do for arithmetic. So it says, fortunately, there's a shortcut formula. We're really not going to use the shortcut formula because we could just use our summation on the calculator. But we are going to use one when we get to infinite geometric series. These 2 words are important to know. Diverge versus converge. So diverge means something is getting bigger and bigger and bigger, or the one I had on the board, it was getting smaller and smaller and smaller to negative infinity. So it diverges if you keep adding larger and larger numbers, because it's either going to approach positive or negative infinity. So it's diverging. It's going further and further and further. But converging means that it's going to approach a specific number. It's going to converge to 8, or it's going to converge to 100. If it's going to approach a number other than positive or negative infinity. So I'm going to show you how you can tell if it's going to converge or not. So here's just a series that we're going to look at just as kind of an intro. 200, 100, 50, and 25. So it says, what is a sub 1 in this series? A sub 1 is just 200. And what is r? 1/2, right? I'm multiplying by 1/2 every single time. So it says, let's write out the first 4 partial sums. So the first partial sum, I just take the first term. The second partial sum, s sub 2, I'm just adding the 200 plus the 100, right? The third partial sum, 200, 150 would be 350. And the fourth partial sum adds up to 375. So we're going to study what this number is doing. So is this number going to keep getting bigger and bigger and bigger forever? Or is it going to converge to a specific number? And it says this series is actually going to converge. So if we keep going a little bit higher and a little bit higher and a little bit higher, it's going to get really close to a certain number. So let's just figure out first what it's going to converge to. So I just want to take this summation and try going to like maybe the 8th partial sum or the 10th partial sum. We don't have to go all the way to infinity. So if I just take let's do the 8th partial sum. So n goes from 1 to 8, and this is 200 times 1/2 to the n minus 1 power. It's important we remember how to write a geometric sequence, right? The n minus 1 power goes in the exponent. That gave me 398.43. So let's plug in a bigger number. How about we do the 20th partial sum? So if I go from the 8th partial sum to the 20th partial sum, I'm adding on 12 additional terms, right? That's a lot of extra numbers to add on. And let's look at how much we changed by. We only changed by a couple fractions, right? Right? 398.4 to 399.999. Now, what if I try the 50th partial sum? You don't have to go too far before your calculator says that's too many digits. So by the 50th partial sum, your calculator can't do anymore. It's going to be 399.9999999. Your calculator, it doesn't get to 400, but your calculator says that converges to 400. If you have enough 0.9999s forever, your calculator is going to tell you that 399.99 repeated is 400, just like 0.6666666 is the fraction 2/3. So that's what it means to converge. It's approaching a certain number, even though we only get to 399.999 repeated. It said it converges to the number 400. So I'm going to prove to you why it is. You don't have to really memorize the proof. I just want to show you that they didn't take it out of thin air. They actually proved why this works. So this is just representing what we did above, but instead of writing, you know, the number 200, the number 100, they're calling the first term a sub 1, and then r to the 0 power is just itself, right? So a sub 1 is the first term. This takes a sub 1 again and adds the term 100, right? Because we're taking 200 times the ratio a half. So this is just going further and further out, right? This takes the first term each time. This times it by a half, times it by a half squared, times it by a half cubed. So this is basically the general form of just what's up above. Do you see that? So they're going to take this and do a little proof on it. And I think we haven't done a lot of proofs, so it doesn't hurt you to write it out, but if you'd prefer to just watch, that's okay. I want to prove what S sub n is. So I want to prove what is this summation for any geometric sequence or series. All right, so let's just write it out one more time. S sub n is equal to a sub 1 r to the 0 plus a sub 1 r to the first plus a sub 1 r squared plus, if I just keep going forever, eventually I'm going to be at a sub 1 r to the n minus 1 power. Whether I go to, you know, s sub 7, that would be the 6th power, or s sub 100, that would be the 99th power. So this is just any sequence, right, would end with n minus 1. So someone smarter than me came up with this proof. So they decided, I'm going to multiply this entire equation through by r. I wouldn't think to do that. So this is just a proof. You don't have to know I would multiply by r. So what they did is they went through and said r times s sub n. If I multiply by r, what's it going to do to each of these r powers? Like, what would happen to the r to the 0 power? R to the first power, right? Because I multiplied by r. What would happen to r to the first power? R squared, r cubed. What would happen to this last term? This would just become r to the n, wouldn't it? Because you're multiplying it by r. So we're just going to rewrite this as a sub 1 r to the first, right? I just changed that by 1 power, plus a sub 1 r squared plus a sub 1 r cubed plus a sub 1 r to the nth power. So all we've done is multiply through every single thing by r. So then what they did is they subtracted the top row minus the bottom row. So that gives me s sub n minus r times s sub n on the left. And can you take a look at when we subtract this bottom row, right? Aren't those two things going to subtract from each other and go to 0? Aren't those two things going to subtract from each other and go to 0? And actually, won't everything subtract with a partner except for this guy, right? And except for this guy. They're not going to get a partner to subtract from. Are you with me kind of so far? So what I have left is I have this term, a sub 1 r to the 0 power, minus a sub 1 r to the nth power. What is a sub 1 r to the 0 power? Can I just call that a sub 1? Because r to the 0 power is just 1. All right, so we're almost to the end. Next, they factored out s sub n on the left side, because our whole point is, how can I find the sum of whatever, the 7th partial sum, the 10th partial sum? If I factor out s sub n, I get 1 minus r, right? Because anything divided by itself is 1. And then if I take the s sub n out, I'd have minus r. So I factored the left-hand side. What could I factor out on the right-hand side? Don't they both have an a sub 1? So I would have 1 minus r to the n. So all I did was I kind of simplified by factoring out the greatest common factor. And then the last step is divide through by this 1 minus r. So S sub n is equal to a sub 1 times 1 minus r to the n over 1 minus r. So before they had a calculator that could do summation, they had to rely on this formula in order to do a finite geometric series. If I wanted to add together 100 terms, I didn't have to actually add together all 100 terms. All I needed was the first term, I needed the ratio, and I needed the n value. Let's say n was 100. So this actually made the calculations a lot easier for someone that didn't have a special graphing calculator. They could do this on a scientific calculator, right? All they need is the first term, and they need the ratio, which might be a half, and they need the n value, which could be 10 or 15 or 100. So this allowed them to do these calculations without needing the summation. We really don't need this formula. We're just going to use the summation on the calculator. But the reason I wanted to show you this formula is because we are going to use it now to get our infinite geometric formula. What happens if n is a really big number? If n is a really big number, what would happen if this was a fraction like a half? What's a half times 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 a half? Basically very, very small, right? So what happens is when you have a really big number for n, like infinity, this numerator just becomes 1. And 1 times a sub 1 is still a sub 1. So I just wanted to show you where this formula comes from. They're not just pulling it out of thin air and it magically works. They actually proved it out from the finite series, and then they just inflated the n value to like a million. So this is going to be the formula that we're going to be using a lot. I can't prove it to you like I did the pairs, but I semi-proved it to you, and now we're going to accept that this is the formula for any infinite, so it goes on forever. It's a geometric series, but it converges. So you're multiplying by a half, or you're multiplying by a third, or you're multiplying by 5/6. It has to be less than 1 for it to converge. So let's try it on the one that we did on the front page. What was a sub 1? A sub 1 was 200, right? Let's see if the formula works. If I take 200 and I divide by 1 minus the r value, which was 1/2, do I get the correct answer? Isn't that 200 divided by a half? When you divide by a fraction, you multiply by the reciprocal, right? 200 times 2 over 1 is 400. And that's what we thought it would converge to. So it's a really cool formula. It allowed people to do these calculations without needing these really fancy scientific graphing calculators. So that's kind of our fourth and final formula, is that you take your starting term and you divide by 1 minus the ratio. Only if it's going to converge, it'll tell you what it converges to. So I want to take a look at using that formula on 7, 8, and 9 first. I'm just going to jump to the bottom on page 510. First, I want to know, is this going to converge? Because see how they're all going to infinity on the top? The only way that you can evaluate it is if it's a converging series. So you look at your ratio. If my ratio is 0.6, will it converge? Yes. What's my ratio on this one? 1/2. So that will converge. What's my ratio on this one? -1/2. So that will converge. So the only time it'll converge is if your ratio is less than 1. If your ratio is 2, you just say that it diverges. You can't solve the problem. So let's use our formula just to practice it for a minute. Oh, if you notice, do you see how they started n equals 0 as the first term? That's really not a problem. Do you see what they put for their exponent? Instead of putting n minus 1, they just put n. So sometimes your summation might start at 0, but they might put n instead of n minus 1 to account for that. So let's do our formula. A sub 1 over 1 minus r. What's a sub 1? If I plug in 0 here, isn't the first term going to be just 4? And then what's 1 minus 0.6? 1 minus 0.6 is 0.4, right? So you're taking 4 and you're dividing by 0.4. If you want to do it on your calculator for this one, that's fine. So what's 4 divided by 0.4? 10, right? Because 4 divided by 4 is 1, and then move the decimal place. All right, try 8 and 9. On number 8, you'll have to think about what the first term would be. On number 9, you'll have to think about using a negative ratio. See if you can use that same formula. Take your starting term, divide by 1 minus the ratio. So I'll give you just one more minute to try those two, and then I'm going to have you try kind of the top problems and the back page. Most of these aren't new. They're just using summation on your calculator. That's why I did the couple new ones with you, the infinite ones. On number 8, if you plug in 0, anything to the 0 power is 1. So the first term would have been 1, and then you're doing 1 minus a half. So the answer should have been 2 for this one, right? Because you're taking 1 and you're dividing by 1/2. So if you are unsure, what you can do in your calculator is put in a large number. So if I wanted to go, x goes from 0 to like 100, and then I could do 0.5 raised to the nth power, your calculator can do it 100 times, and it basically will tell you what it converges to. So you can check infinite summation on your calculator. Just plug in a big number like 100. Don't plug in 1,000,000 because your calculator will just like freeze up. Be like, I'm not going to do this 1,000,000 times. But if you do 100, it'll work. This one also would have a starting term of 1, but when you take 1 and subtract negative 1/2, you actually get 1.5 in the denominator. So you're taking 1 and you're dividing by 1.5. Maybe you know what that is as a fraction, right? Because you're taking 1 divided by 3/2. So flip it, multiply by the reciprocal. It would be just 2/3, right? 0.66 repeating. Did you get that for number 9? All right, so go on through, go back up to the top. You've got 1 through 6, and then there's also some practice onto the back. Some of the ones on the back are actually arithmetic. So go back, and this is kind of more like the quiz when they're jumbled together and you have to figure out if they're arithmetic or geometric. The quiz is until Thursday. So tomorrow we're going to spend more time reviewing and practicing. All right, so I will come around with an answer key, but I think we should be able to finish 510, the front and the back, by the end of class. You've got 2 nights to complete homework. It's called homework 5-5 on your unit plan. It really is our 4th homework assignment. It was just a typo, my fault. So just the next homework assignment. Okay, and here are the answers to the guided practice for when you want to check your answers. And here's the guided practice for the back. Thanks.